All right, looking at page 69, we have the chi-square test for homogeneity, independence, and goodness of fit. This basically refers to any kind of tabular situation. Well, maybe not any kind, but a good chunk of them are. We think about a chi-square test as being appropriate when you're dealing with more than two population proportions. All right, so if you think back to the two population proportion instance, I think it was the football question, where it was you had a success number of trials for one group, success number of trials for a second group. What if you had success number of trials for a third group, a fourth group, and so on? That's when a chi-square would come into play. Right? We have one-way tables, which is just the trials and successes for one population, I guess, compared to another. So population one, population two, success, number of trials first, then success, and then we do a comparison. If you had three populations, 4, 5, 6, that it would be a longer table, but it would still be a one-way table. It's when you incorporate a second variable, right? So I threw in this a table that shows a comparison among two different categories. So the categories here would be sexual intercourse and gender. So you have two variables, but each one could have a more than one or two populations associated with them. It's just in this case, because I framed it as a yes/no situation, I didn't throw a maybe in there. We would be limited to just the two possibilities within that category, but it could go on and on. If you think about it as like, I think this was in the second unit, the grade ranges like A, B plus, B, C plus, and so on, based off gender or any other category you could think of. That would be another example of a two-way table. So when we did conditional probability, we actually worked with these two-way tables. It's just not, in a different context. So yeah, aggregation. Sometimes you'll see aggregation as an option. And what we can do with this is we can basically pare down a two-way table into a one-way table if we only were concerned with just one of those categories. So in the first case, I had 3 levels of a math curriculum and the pass-fail rates between them. And then if I aggregated it, I just look at math in general. So the issue here is, and it kind of goes both ways in terms of what you do with this, because you could look at it and say, well, you're losing all this information if you aggregate. But then maybe that's the point. Maybe you're trying to push through a policy based off of the fact that students typically pass math courses at this location. Or maybe you were trying to prove or push through a different policy based off the fact that depending on what level math you're in, you're more likely or less likely to pass, right? So it really just kind of boils down to what you're doing with it, right? So when I say, what does this table tell you? It tells you the passing percentage or passing rate. What does it tell you about the usefulness of aggregation? Well, it simplifies down to one category, which simplifies computation. Simplifies computation. The drawback is you lose information. Right. But maybe you either intentionally want to lose information, air quotes lose, or maybe that extra or you might even call it extraneous information, is irrelevant to whatever your research question is. Right. So we'll start off with a hypothesis test related to one-way tables. I have this chi-square distribution table. I'll get back to that in a couple minutes, but for now we're just going to kind of leave that be. The chi-square distribution is a skewed distribution. Right. it it's most closely associated with a skewed distribution. There are some chi-square distributions that are more not uniform, wrong word, sorry, symmetric. It's just we kind of go with the poster child of the chi-square distribution, which is something that's heavily skewed to the right. The critical value is going to be associated with the alpha value. So alpha is equal to whatever. All right. So I'll just label that alpha. All right. So your critical value comes from your significance level. The lowest value in the chi-square distribution is 0, so we're only dealing with positive values beyond the 0. All right. And the center of the hump is your degrees of freedom. All right. So when we draw a diagram, it's going to look like that. All right. Null and alternative hypotheses, a little bit of a departure from what we've been doing. The null is independent or versus an alternative of dependence. A good fit for a population distribution versus not a good fit. Right? So it's just basically whatever you put in a null, just negate it for the alternative. But then that makes this one kind of weird because in a 2 population proportion, it was P1 equals P2. But now I could have equal to P3 equal P4 equal P30. Right? The alternative would not be that they're all unequal, just that at least one of the population proportions is different from the rest. Slight difference in degrees of freedom. K represents the number of categories, so K minus 1 would be your degrees of freedom. We have a nice formula here that we're not going to have to use because the calculator is going to handle it for us. We state the conclusion, same deal. And again, this is a chi-square distribution. So even though it looks like an x squared, it's really a chi-square. All right. So let me take you to an example. A die is rolled 60 times, and the following results are documented. All right. So we got a 1 14 times, we got a 2 15 times, we got a 3 10 times, and so on. Now, it should have been 10 for each of them, right? When you roll a die 60 times, if each outcome is equally likely, then they all should have been 10s, right? That's what we expected. You know, maybe a little wiggle room from here and there, but what the chi-square is going to do is figure out, all right, on average, are we close enough to those expected values to say that the die is fair, or are we far enough away in certain instances to say, well, this is a little out of whack. So I'm looking to show through the chi-square distribution that the probability of getting a 1 is the same as the probability of getting a 2, 3, 4, 5, 6. And that the alternative would be at least 1 population proportions not equal. All right. This first outcome, this first set here, would be the instance that the die is fair. Die C. Oh, that's a new one for me. Die is fair. Die is unfair. Because if it's a fair die, all those probabilities should be the same, or at least close enough to being the same. All right. So for my statistics, I could come up with the chi-square values, but really and that's going to be done in the calculator. And I don't know that there's really much more to write here than to say the degrees of freedom, K minus 1, is going to be, there's 6 categories, minus 1, 5. Plop that in the middle. So that's a 5, that's a 0, and somewhere over here is my critical value for chi-squared. All right. So if I go into my, we'll just focus on the critical value. If I go into my calculator and look at my distributions, so you have the normal, student T, binomial, Poisson, geometric, and hypergeometric. It does not give us the chi-square distribution. All right. So we run into a little bit of a problem there, which is why, and you can, scour the rest of the list looking for it. If you find it, let me know, because I haven't found it. But if you go into inference, test, go to chi-square. This is the goodness of fit test for a one-way table. Use chi-square GOF test, goodness of fit test. And you put in your observed values, 14, 15, 10, 8, 7, and 6. And then 10s across the board or down the line here. Degrees of freedom 5. Thank you, calculator. It recognized that because I put in 6 entries. I have 6 categories, so therefore my degrees of freedom should be 5, so that's nice. 0.05, they did tell us 0.05. I sort of glossed over what the question was asking. Does this data cast doubt on the fairness of the die at the 5% level? All right. So there you go. They give me the chi-square test statistics. So chi-square. They don't give me much more than that and the p-value, which is honestly all we really need. But, 2, 2, 1. All right. The p-value is not less than the alpha value, so do not reject HO. So the HO is good. The HA not so much. I'll go to next. You see, it's the same deal. They don't give us that cutoff associated with the alpha value. They give us the test statistic, but not the cutoff. That's where that table comes into play. So if I go to my table here, which for a question on a test, you'd need this table, and so I'd give you this table, we just find degrees of freedom corresponding with the alpha value, right? So the 5 degrees of freedom, the alpha value 0.05, 11.071, right? So that should be my cutoff, right? So there is insufficient evidence to reject the claim that, well, the null hypothesis was that all the probabilities were equal, that the population proportions for each outcome in the roll of a die are equal. That's what the null is saying. At the 0.05 significance level, that addressed the null hypothesis. Oh, sorry, I put it on. There is insufficient evidence, but for some reason that I can't explain just now, that I don't have the answer to, I crossed off the wrong thing. All right, so there's insufficient evidence to reject the claim that the population proportion for each outcome in the roll of a die is equal. I guess that's why people proofread stuff. At the 0.05 significance level, therefore, well, they were only asking us about whether the die was fair, right? So here, I mean, I've just flat out said it, the die is fair. If this was true, then this would be true. I never really answered that, so we could then just make a follow-up, because we don't need the second sentence here. We could say the die is fair.